Hello everyone, welcome to the Modeling Guy. Have you ever wondered what the real difference is between linear and nonlinear finite element analysis? In this video, we will break down when to use each, why it matters, and how choosing the wrong one can totally change your simulation results. Stick around till the end. I'll share a quick tip to help you choose the right finite element analysis method for your next project. If you're watching this video, you probably already know what FEA stands for, Finite Element Analysis, the workhorse behind almost every engineering simulation out there. Now, when it comes to finite element analysis, we usually deal with two main types. Linear analysis, where everything behaves nicely and proportionally, and nonlinear analysis, where things get a little more interesting and a lot more realistic. Alright, so what actually makes a linear analysis different from a nonlinear one? Let's break it down step by step and look at the 11 key differences that every FEA engineer should know. At a mathematical level, the main difference starts with the assumptions. In linear analysis, we assume everything stays constant, whether it's material properties, geometry, or boundary conditions. But in nonlinear analysis, those things can change as the load increases. The material may soften, the shape can distort, or even the constraints can shift. In a linear analysis, the geometry never changes. We always solve using the original undeformed shape. But in nonlinear analysis, the geometry keeps updating as the structure deforms. This makes the results more accurate, especially for problems with large displacements or rotations. In linear analysis, the stiffness matrix is built once, and that's it. But in nonlinear analysis, the stiffness matrix keeps getting updated in every iteration because the system response itself changes as the load increases. That's what makes nonlinear simulations much heavier but also much more accurate. In linear analysis, solving the system is straightforward. You invert or decompose the stiffness matrix once and get the result in a single step. But in nonlinear analysis, the solution requires multiple iterations. Each step refines the result until the equations finally converge. That's what makes it computationally intensive. Linear analysis is fast and efficient. You solve the system just once and you're done. But nonlinear analysis takes a lot more computing power. Because of all those iterative updates, it can be 10 to 100 times more expensive in terms of time and resources. In linear analysis, we assume the geometry barely changes. Only small deformations and tiny rotations. But in nonlinear analysis, the geometry can change drastically. Think large bends, twists, or displacements where the updated shape actually affects the next step of your solution. In linear analysis, all the loads are applied at once, and since everything scales proportionally, the principle of superposition applies. But in nonlinear analysis, loads are applied incrementally, step by step by step. Each load step changes the stiffness and response, so you can't just add results together anymore. In linear analysis, the solution is exact. It always converges because the equations are simple and predictable. But on nonlinear analysis, convergence isn't guaranteed. The solver must iterate until it meets strict convergence criteria, and sometimes it just doesn't. In linear analysis, the boundary conditions stay fixed. Supports, contacts, loads never change during the simulation. But in nonlinear analysis, the boundaries can evolve, new contacts can form, existing ones can separate, and constraints can update as the model deforms. Linear analysis is lightweight. It needs less memory and storage since the system is solved only once. But nonlinear analysis is much heavier. Each iteration, every load step, and every geometry update adds to the memory and file size, making it far more data intensive. So now that we have seen how linear and nonlinear analysis differ, let's talk about when to use each one. Starting with the linear analysis, it's best suited for problems involving small deformations, elastic material behavior, and no contact changes. You'll often use it during early design stages or whenever linearity is a fair assumption and you just need quick and reliable insights. On the other hand, nonlinear analysis is essential when reality refuses to stay simple. You'll need it for cases involving large deformations, material yielding, buckling, or complex contact interactions. It's also the go-to method for dynamic impact events where linear assumptions completely break down. In short, nonlinear analysis gives you more accurate and realistic predictions for these challenging scenarios. So, to wrap things up, while linear analysis helps us simplify and understand the basics, it's important to remember that the real world rarely behaves linearly. As Professor Ted Belytschko beautifully put it, linear analysis is only a first approximation. The real world is nonlinear. Whether you're designing aircraft components, simulating crash impacts, or modeling soft tissue deformation, the closer you get to reality, the more nonlinear your world becomes. Thank you so much for watching this video. If you found this helpful, don't forget to like, share, and subscribe for more videos that make complex modeling concepts simple. See you next time.